Alrighty, gang, welcome back. So congratulations on surviving the test. You took the test in the testing center. I just grabbed all that stuff from them yesterday. I'll be working on getting those graded as soon as I can. My usual rule for test turnaround is about 1 week. So my goal for you guys would be to have the test graded by Wednesday. Today we're going to move on. I will be publishing a new homework set for you guys today. I'll give you a little bit of extra time to work it. Probably not going to be due next Monday. Probably will be due next Wednesday, just to make sure you have a fair amount of time on it. The material that we're moving into now, so the first part of the course is like limits and the concept of a derivative and just kind of trying to get you okay with the basic idea of what a derivative is and how to compute derivatives for very nice functions. The next part of the course, the kind of middle third of this course, is all about applications of the derivative. So things you can do with derivatives. And the last part of the course is going to be on a totally different problem, but turns out to connect back in a cool way. So today we're going to look at our first little taste of things we can do with derivatives. The topic is called implicit differentiation. So let's dive in and I'll show you what I mean. This, of course, is MAC2311, section 0H1, which is Calc 1 honors. And today is the 1st of October, 2021. Today, we're going to talk about implicit differentiation. I forget what section this is in the textbook. It might be 4.1. No, I think it's still in chapter 3. What is this section? 3.5. I'll tell you right now, this is a section people often have trouble with because it's not super obvious at first how it's working, and some of it can feel a little bit weird. The truth is, though, it's really just a consequence of the chain rule. So implicit differentiation is just another way of writing the chain rule. I'm burning up in here, so I'm going to turn on the air real quick. I'll be right back, and we'll get started. Alrighty, here we go. So first, the word implicit. Does everybody know what the word implicit means? It's the opposite of the word explicit. So implicit comes from the word imply, which is to like suggest without saying directly. So it's a kind of indirect differentiation. So implicit differentiation is a indirect way to get the derivative y prime from what are called implicit expressions. Those are equations not solved for y. So I want to show you an example of an implicit expression and compare it to an explicit expression, and then we'll look at how to do implicit differentiation. And we'll see that it yields the same answer that you would get if you differentiated explicitly. But sometimes you can't differentiate explicitly. Sometimes you have an equation where you cannot solve for y. It's not possible. So you need to use implicit differentiation. This will be especially useful for cooking up derivatives of things like inverse trig functions. So implicit versus explicit expressions. I should say functions. So if I say y is equal to 1 over x squared plus 1, this is an explicit function or explicit expression. And we can find y prime the normal way. Right? Y prime would be what you get when you take the derivative of 1 over x squared plus 1. But you could do with the quotient rule, or you could do it with the chain rule here. There's a bunch of ways. I'll just do it real quick with the quotient rule. So that's bottom times the derivative of the top. The derivative of the top is 0. I'll write it up, x squared plus 1 times 0 minus the top times the derivative of the bottom, all the bottom squared. So this would be negative 2x over x squared plus 1 all squared. So I'm starting with an explicit definition of the function, right? Y is defined to be a function here. The function is 1 over x squared plus 1. So we can calculate y prime just by taking the derivative of that function, and we get this. On the other hand, if I had, say, x squared y plus y equals 1, this is an implicit expression. So this equation right here does define y as a function of x implicitly. You know you could, in theory, solve this for y, and you would get this. We can get y prime using the chain up here. Here's how it works. I take this equation and I differentiate on both sides with respect to x. I take d dx on the left, x squared y plus y, and d dx on the right. I'll get a true statement because I'm applying the operator d dx to both sides of this. And somewhere in this mix, I will get my derivative, y prime, dy dx. d dx of 1 is 0. And on the left-hand side, I can use my rules. This would be d dx of x squared times y plus d dx of y. d dx of y, that's the derivative of y, taken with respect to the variable x. So the understanding here again is that y is secretly a function of x. So this would just be y primed. And here you would need the product rule. So d dx of y is just y primed. d dx of 1 is 0. I'll put that up here too. Of course, d dx of 1 is 0. And then the other piece we have is d dx of x squared times y. And this requires a product rule. This would be x squared primed times y left alone plus x squared times y primed. The derivative of x squared taken with respect to x is 2x, so I get 2xy plus x squared. The derivative of y is just y prime. So altogether over here, what I have is 2xy plus x squared y prime plus y prime equals 0. And believe it or not, this will give me the same thing that I got up here if I solve it for y prime and plug back in this y, knowing that y is 1 over x squared plus 1. Let's do that. So I can subtract the 2xy over, I get x squared y prime plus y prime equals negative 2xy. I can factor y prime on the left. X squared plus 1 times y prime is equal to negative 2x. And I plug back in for y here. Y, remember, is 1 over x squared plus 1. And now if you divide both sides by x squared plus 1, you get y prime. I'll put the negative 2x up here. 2x over x squared plus 1 divided by x squared plus 1 is times the reciprocal of x squared plus 1. So again, we get y prime equals negative 2x over x squared plus 1 times x squared plus 1 is x squared plus 1 quantity squared. Same thing. Now, obviously, the second thing took longer. Had to write more. Some of the steps felt a little strange. So you'd be wondering, why would anybody ever do this stuff instead of just doing the thing that we did before? The answer to that question is sometimes you have an equation like this where you can't solve for y. If you want to differentiate to find y prime, you can still do that. What we're leaning on here is something called the implicit function theorem, which says if you have some equation involving x and y, you can assume that it could, in theory, be solved for y. You can pretend like you know how to solve for y, or like somebody knows how to solve for y. So y really is implicitly a function of x. But you don't need to solve for y in order to take your derivative. So if you are unable to actually solve for y, you just assume that it is hypothetically doable, even though the algebra steps can't be done, and take the derivative this way. And then you solve for y prime. So sometimes, even if you have an equation like this, but couldn't solve it for y, after taking the derivative, you can solve for y prime and get an explicit form of that derivative. Or sometimes you just have to suck it up and accept that you've got an implicit form of your derivative and deal with that instead.
I have a question here. How did you know the y is 1 over x squared plus 1?
So this is the equation I started with here, right? The difference between this and this, I got this just by cross multiplying the x squared plus 1. So you could say, oh, I'm going to go back and solve this for y. This is, if you solve for y, you have x squared plus 1 times y equals 1. So y equals 1 over x squared plus 1. So this is an example where I could solve the original equation for y, right? That was the idea. We wanted to do this 2 different ways. So this last step here, plugged in this for this y. We could stop here, all right? That's another option. If you can't solve for y, if you can't solve the original equation, for y, we can leave y as y, and that I can still solve this for y prime. So then I would have x squared plus 1 times y prime is equal to negative 2xy, which means y prime would be negative 2xy over x squared plus 1. So this would be an implicit form of the derivative. This would be the explicit form of the derivative. The only catch here is if you want to then do something with the derivative, if it's in an implicit form, you need to plug in for y's and x's separately. You'd have to figure out what y's are associated with a given x. I think it's wise, before we poke too much more at this, and to just look at the basic rules as they're going to show up. So that's the big idea. The big idea is an equation involving x and y defines y as a function of x. Even if we can't or don't want to solve for y. So we can differentiate both sides of such an equation with respect to x assuming that y is equal to f of x for some function f. And use the chain rule. So basically we treat y as our inner function in each of these. And the derivative of y, d dx of y, is y prime. Useful facts. If y is an implicit function of x, then d dx of y is y prime, or dy dx. You can write it either way. Some people like to write dy dx, some people like to write y prime. D dx of y squared. Well, remember we said y is like the inner function, right? This is like f of x all squared. So I'm assuming y is a function of x. So the outer function here would be the square, the inner function here would be the y. So this would be 2y times the derivative of the inner function, y prime, or 2y times dy dx. D dx of y cubed. Similar. Y is like the inner function, so we differentiate the outer function, leaving the inner alone. That's 3y squared, leaving the inner y alone. And then you multiply by the derivative of y, which is y primed. So this would be 3y squared times dy dx. Operationally, the way it works is you just slap on a y prime, right? You differentiate like you normally would, but then you slap on a y primed. I can show you some other sort of very basic examples here that we will use as pieces quite often. If I wanted to take d dx of the sine of y, I can do that. I would differentiate the outer function, which is the sine function, leaving the inside alone. and then multiply by the derivative of the inside, which is just y prime. Right, you get the idea. d dx of the square root of y. I treat that as a 1/2 power, so that would be 1/2 y to the negative 1/2 times y prime. We getting the feel? So it's kind of like differentiation is normal. It's just that every time you differentiate the dependent variable, which we usually use y, every time you differentiate a piece involving the dependent variable, y, you take the sort of normal derivative and then you multiply by y primed. Or you can say take the normal derivative and multiply by dy dx if you prefer the Leibniz notation. This sort of notation on the far right here, which I didn't give the alternate notation for these two, this is actually the notation we're going to be using when we talk about related rates. So even if you don't love it, and I'm in that camp, I don't love this notation because I think it takes a lot of extra writing. We will need it when we talk about related rates because we'll have different variables and you want to be very clear. The prime doesn't tell you what you're differentiating with respect to. Okay, let's look at a nice simple example problem. Let's find the equation of the tangent line to the circle x squared plus y squared equals 4 at the point root 2 comma root 2, which I promise you is on that circle. Yeah. So here, let me show you in Desmos really quick. Oh, I'm zoomed way out. Sorry, I was doing some improper integration to pick out 2 kids this morning. Okay. Zoom out a little bit. All right. The point square root 2 comma square root 2. Oh no, that's 2 root 2. Yeah, root 2 comma root 2. It's right there. So I want to find the equation of the tangent line to this circle at that point. Right? And this is worth doing implicitly because solving this for y is kind of nasty. Right? If you wanted to do this explicitly, you would have to solve this for y. You would get y equals plus or minus the square root of 4 minus x squared, which is kind of nasty. Let me make a quick note. To do this without implicit differentiation, we'd have to solve x squared plus y squared equals 4 for y, and you get y equals plus or minus the square root of 4 minus x squared. Then choose between the plus or the minus, will then differentiate with the chain rule, which is kind of nasty. Right, the derivative there isn't especially nice. And there's this issue of taking the square root and getting the plus or minus. Because this point is in quadrant 1, we know the y value there should be positive. So we would take the positive square root of 4 minus x squared. But then you still have to differentiate that with the chain rule. It's a little bit nasty. On the other hand, doing this implicitly, we know what we need, right? To find the equation of the tangent line, you need a point. We've already got the point, and you need the slope. The slope is going to come from y primed, dy dx. So I apply the operator d dx to both sides. X squared plus y squared equals ddx of 4. On the left-hand side, using my rules, that's ddx of x squared plus ddx of y squared. And on the right-hand side, ddx of 4 is definitely 0. ddx of x squared, it's the normal derivative of x squared, that's 2x plus ddx of y squared is 2y times y prime, or 2y times dy dx. I'll write it as 2y times y prime. Okay. So y primed, I subtract the 2x over here, divide by 2y, is negative x over y. And this is an implicit expression, right? Again, if I wanted an explicit expression for y prime, I would have to take this and plug it in down here. But I don't care, because I'm just after the slope of my tangent line, and I know the point. So m tan, right, the slope of my tangent line, is y prime at that point, root 2 comma root 2, which is negative root 2 over positive root 2, which is negative 1. This notation, if you haven't seen it, just means evaluated at this point, right? So we're going to take this y prime and plug in root 2 and root 2 for x and y. And that's it. Now I've got a point and a slope. Here's my point. Here's my slope. Therefore, the tangent line is y minus the square of 2 equals negative 1 times x minus the square root of 2. Using the point slope formula again. Okay, and you'll see here, if I type that in, there's your tangent line. Not bad, right? So implicit differentiation is a useful tool when you're trying to do normal derivative stuff, but you don't have a function like y equals f of x. You have some equation that defines y as a function of x. And it's especially useful when you either cannot or do not want to solve for y in that original expression. Either because when you solve for y, you get something that's hard to differentiate, or because you cannot solve for y. There are many equations that cannot be explicitly solved. Questions on this example? Okay. So you will have stuff like this in your homework, right? Find the equation of the tangent line, blah, blah, blah. More exciting, I think, is some of the other stuff you can do with implicit differentiation. Like we can use implicit differentiation to find the derivative of inverse trig functions. Let me say recall the inverse trig functions are defined. I'll just do like inverse sine tangent to get started, right? This is the vibe. So we say y is equal to the inverse sine of x, or y is equal to the inverse tangent of x, if and only if the sine of y is equal to x, and we also need y, my angle, to be restricted from negative pi over 2 less than or equal for sine, less than or equal to positive pi over 2. The definition of the inverse tangent function, all of you went through that quiz with me, so hopefully we remember these. Tangent of y is equal to x. Negative pi over 2 is strictly less than y is strictly less than pi over 2. We'll do one more. Let's do the inverse cosine function. His definition, y is equal to the inverse cosine of x, means that the cosine of y is equal to x, and his restriction is different. 0 is less than or equal to y is less than or equal to pi. Each of these restrictions comes from wanting to make the original trig function 1-to-1, right? So sine is not a 1-to-1 function. Tangent is not a 1-to-1 function. Cosine is not 1-to-1. But you can make them 1-to-1 by narrowing their domains down enough. All right, so just to start, remember, these are the definitions of these functions. Secant and cosecant can also be rewritten as inverse trig functions with their own domain restrictions. So we can use implicit differentiation to find, for example, ddx of the inverse sine of x. All right, I want to take this guy and find y prime. But I don't know the derivative of the inverse sine function. I can't just say, all right, well, y prime is equal to the derivative of this thing. I don't fucking know what the derivative of that thing is. But y is equal to the inverse sine of x is the same as saying sine of y is equal to x as long as you're within this domain. So we're going to do this implicitly. Equals sine inverse x, and I want y prime. Well, y equals inverse sine of x is the same as saying sine of y equals x. And of course, y is between negative pi over 2. So what I'm going to do is I'm going to apply the operator ddx to both sides here. ddx of sine y is equal to ddx of x. And on the left-hand side, ddx of sine y is cos y times y prime. It's just the chain rule. You just have to remember that y is secretly a function of x. And on the right-hand side here, ddx of x is 1. So y primed is 1 over the cosine of y. But that is not super satisfying, is it? So what I want to do is rewrite this as a function of x. I would like to get an explicit form for this derivative that doesn't depend on y. And the only way I can do that is to rewrite cos y using this stuff and a triangle. So this is correct. But to get an explicit expression, we should replace cos y with some x stuff. So how can I find the x stuff that is equivalent to the cosine of y? There's a lot of ways to do it. I think most people would say draw a triangle. So draw a triangle using the fact that sine of y is equal to x. X is the same as x over 1. So I can use SOHCAHTOA to draw a little triangle here where y is that angle down there. Sine is the opposite over the hypotenuse, right? That's your SOHCAHTOA. So your opposite side length here should be x. Your hypotenuse here should be 1. And solving this triangle, this missing side. Solving this triangle for the missing side, you get square root of 1 minus x squared. Yeah, solve for this. So right, so you write x and 1 here, you could label this as like b, and you know that a squared plus b squared equals c squared. So this missing side length down here is the square root of this squared minus the squared.
I have a question. I hear you draw a triangle and the sine y is equal to x over 1. Is it because in the top you already know the sine y is equal to x?
Yes.
So you just okay.
Yep.
Thanks.
That's where I'm getting this from. So sorry, let me state that explicitly. So remember, my goal is to find cosine y in terms of x. I know that sine y is equal to x, so I can take that, call x over 1, and use it to draw a triangle. This is something that hopefully you're familiar with from your trig class, but if you haven't seen it in a while, here it is. All right, so now.
Wait, super quick reminder how you found that missing side on the triangle?
Sure, yeah, let's come back here. All right, let me come back here and just call this thing A. Missing side length A. Then I know to solve for that, I know that a squared plus x squared should be equal to 1 squared, right? That's my normal Pythagorean relationship.
Oh, right. Yeah. I knew there was some kind of a policy. I just couldn't remember it off the top of my head.
Yeah, no worries. So then a would be the square root of 1 minus x squared. Taking positive squares because it's a side length. That's nothing too fancy. So now I can read off the cosine of y, right? I have a triangle here, a right triangle here, where the internal angle is y, and I know all the side lengths. The adjacent is 1 minus the square root of 1 minus x squared. The opposite is x. The hypotenuse is 1. So y prime is 1 over the cosine of y must be, well, what is cosine of y? Cosine of y is the adjacent over the hypotenuse. So that's the square root of 1 minus x squared over 1, which is just 1 over the square root of 1 minus x squared. In other words, i.e., and this is something you should remember forever and ever, amen, it's the first derivative of an inverse trig function that we've learned. The derivative of the inverse sine function is 1 over the square root of 1 minus x squared. Cool stuff, right? And we could have never done this otherwise. You need implicit differentiation to do this. I'll do the tangent function. I'll just tell you the result for cosine. Similarly, you'll find d dx of the inverse cosine function. This is negative 1 over the square root of 1 minus x squared. It's very, very similar. You're just going to negative. The other one I want to actually work out for you is the inverse tangent function. I'll just tell you the derivatives of the other inverse trig functions, but the process is the same. Yeah. let's get fresh paper. Find y prime where y is the inverse tangent function. And remember that the -1 up there, that's not a power. This isn't like tan squared. The last one isn't like sine to the -1. It's the arctan. That last guy was like arc sine. So one of the kind of first base confusions we need to conquer. This is not a power. Neither of the -1s in the previous page were powers either. It's just the notation for the inverse trig functions. We'll do the same thing. I say, okay, y is equal to the inverse tangent of x means the same thing as tangent of y equals x. And here again, negative pi over 2 is less than y is less than positive pi over 2. So applying d dx to both sides, we get d dx of tangent y is equal to d dx of x. The derivative of tan y is secant squared y times y prime. I'm differentiating with respect to x, and the assumption is that y is secretly a function of x. And the derivative of x is still 1. So y prime is 1 over secant squared of y. And that's a true statement. It is an implicit statement, though. I would like an explicit statement. So again, I'm going to use this to draw a triangle. Since the tangent of y is equal to x, which is x over 1, I can interpret that as an opposite over an adjacent. And draw myself a little right triangle where the internal angle here is y, and this angle is 90 degrees. This would be x, this would be 1, and we have to solve for the missing side here, which is going to be the square root of x squared plus 1. Right. Again, just Pythagorean. A squared plus b squared equals c squared. So what is the secant of y? Secant of y that would be the reciprocal of cosine, which cosine is adjacent over hypotenuse. So this would be hypotenuse over adjacent. So that's the square root of x squared plus 1 divided by the adjacent side, which is just 1, which is the square root of x squared plus 1. Hence, y prime is 1 over that squared. Or just 1 over x squared plus 1, i.e. the derivative of the inverse tangent function, inverse tangent of x, is 1 over x squared plus 1. And this is another one of those super duper important derivatives. You just got to remember it. Just like the derivatives of the regular trig functions, these will eventually sink in through practice. Another way to help them sink in is to run through these proofs. Right? That's what we're doing here. We're proving that the derivative of this function, derivative of arctan really is this. Okay. All right. We could do more tangent line stuff. Let me take a look in your book and see if there are any fun problems of the sort that we haven't touched yet in 3.5. Those are fun. And This is a little wonky.
What are the derivatives for the other three trig functions?
Yeah, that's a good point. Let's go ahead and write down the derivatives of the other inverse trig functions. They're right here. Actually, rather than me writing them down, I can just show you right here, right? Everybody can see this okay? So here's the remaining ones, right? Inverse sine is what we said it is. Derivative of inverse cosine is the negative of that same thing. Derivative of inverse tangent is 1 over 1 plus x squared, or 1 over x squared plus 1, either way you want to write that. And then cosecant, secant, and cotangent are these. So for secant and cosecant, I remember them like this, right? The secant guy, you've got the x squared minus 1 flipped around under the square root, and then you've got an x here. And then for cosecant, it's the same as secant, just with a negative. And cotangent, same as tangent, just a negative. Okay, I'll hold here just for a second more.
Slight side question. There's a small note on the side of the chart. The formulas for the derivatives of arc cosecant x and arc secant x depend on the definitions that are used for these functions.
Yep, so it depends on
What
the
is that?
domain restriction you choose. Let's take a look in Desmos really quick. So each time I wrote down the definition of one of those inverse trig functions, like up here, in addition to this, I said this, right? We've got this restriction.
Yeah.
The derivative for the inverse secant function does depend on how you choose to restrict the original, right? This is not a one-to-one function. Right? It fails the horizontal line test really badly. But if I restrict it to the interval 0 to pi, that's 1-to-1. And this definition here for the derivative of, or this derivative for the inverse of secant is assuming you're using this restriction. Some people restrict this a little differently. They say 0 to pi over 2 here and negative pi over 2. I know, what do? They do 0 to pi over 2 and negative 3 pi over 2. Less than x less than pi, negative pi over 2 or something. I'm not sure what the other one is. There are other weird ways of restricting this, but the natural one, the one that everybody uses, is 0 to pi, the same as cosine. Cosecant, similarly. You can choose to restrict these in different ways. A more familiar example, like sin x, we always restrict this. We usually look at the green restriction, right? This is the normal way to restrict the sine function to make it 1-to-1. But if I wanted to, if for some weird reason I wanted to restrict to like pi over 2 to, I don't know, 3 pi over 2, or sorry, 3 pi over 2, I could do that too. So I could use this as my restricted domain for the inverse sine function, and that would give me something different than if I use the normal one. So some people use weird restrictions for inverse trig functions, but if you use the standard restrictions, which are negative pi over 2 to pi over 2 for sine and tangent, and 0 to pi for cosine and secant, then these are the formulas you get.
I forgot how do I get the sine to the arc sine and the cosine to arc cosine. I forget how to transfer it.
So those are the definitions that we wrote down a little bit earlier. So the way you get arc sine from sine or arc cosine from cosine, we say that the inverse sine function means sine of y equals x, and negative pi over 2 is less than or equal to y is less than or equal to pi over 2. Or for cosine, we say the inverse cosine of x, y equals inverse cos of x means cos of y equals x and 0 is less than or equal to y is less than or equal to pi. So these are the definitions of the inverse trig functions. They're the functions that undo the trig functions, but they only work within these restricted domains.
So transfer, then just put the because it's y is equal to x sine of x. So I just put the y in the sign and it's equal to x. Just transfer like that.
Yeah, operationally. So when you guys first learned about these things in trig class, usually we do something like this, right? We would say y equals sine inverse of x, and then you would take sine of both sides or something like that. You'd say, so sine of y is equal to the sine of the inverse sine of x. And then you would say on the right-hand side, those cancel or something like that, and get this. It's that cancellation property that most people use, right? That's where these inverse trig functions first show up, is when you're trying to solve equations. And you have to, okay, I'm going to take the inverse sine of both sides to get rid of the sine. I'm going to take sine of both sides to get rid of inverse sine. So for example, solving, I don't know, sine theta equals 3/4, we would say, okay, sine theta equals 3/4. So take inverse sine of both sides, sine inverse of sine theta, sine inverse of 3/4, and then you'd say on the left-hand side that sine inverse and sine cancel, and you just get theta equals sine inverse of, which is not a nice number, right? So the reason we have these inverse trig functions is to allow us to write down solutions to equations like this, even though the number here on the right-hand side is not pleasant at all. And of course, this would just be one solution, right? This would be the single solution for theta, where theta is between negative pi over 2 and pi over 2. And if you wanted all the solutions to that, you would have to extend periodically.
So the secant, tangent, cotangent, and the cosecant, they use the same way with sine?
Yep. Yeah, all the inverse trig functions kind of work in this same way. They just each have their own separate domain restriction.
Thanks.
Yeah, of course. There is a place, I've got a link for you guys to look at some more of this stuff if you want to in the modules. So I think a number of us spoke about this during the kind of skills test before the start of the semester. And if you're looking for more of this, let's see, I think it's in here. The algebra trig review, inverse trig functions. Here's all the definitions, all of the common mishaps, and the associated domain restrictions. It'll all be in here. So this would be a good place to start if you need to remind yourself. All right. So let's look at some other problems we can solve. Some fun stuff, please. That looks good. What do we want to do? Find dy dx by implicit differentiation. Sure, let's do one of these. Let's do something that's not super brutal, like number 8. So x cubed minus x y squared plus y cubed. All right. So they say find dy dx using implicit differentiation. If they didn't say to use implicit differentiation, we could try to solve this for y first. But what you would discover is that it's actually impossible to solve this equation for y. Can't be done. Cannot be done in any nice way. So implicit differentiation really is necessary. And the way we're going to do it is by applying d dx to both sides. And that middle part, the d dx of xy squared, this is going to require a product rule. The other guys are pretty easy, but we want to be very careful here with my product rule, especially since this term happens to be negative. So let me just write it out. This would be d dx of x cubed minus d dx of xy squared plus d dx of y cubed equals the derivative of 1, which is 0. Now, normally I write the little derivative that you have to slap on there as y primed. Since here they said they want dy dx, they didn't say find y prime, I'll write dy dx instead. This piece is easy. d dx of x cubed is a power rule derivative, 3x squared, no implicit anything there. Then we'll have minus, open up a big bracket or parentheses here because this piece is about to be kind of expanded using the product rule, minus. If I apply the product rule to this, first I differentiate the x and leave the y squared alone. So the derivative of x is 1, leave y squared alone, plus leave x alone, and now I need the derivative of y squared, which is 2y times dy dx, or 2y times y prime. And then I've got plus d dx of y cubed, which is 3y times y prime, or 3y times dy dx. And my right-hand side is still 0.
Is the last expression 3y squared dy dx?
I'm sorry, can you repeat that?
Sorry, is the last expression 3y squared dy dx?
3, oh, yes. Thank you.
Okay,
2y
cool.
squared, yes. Yes, very good. Sorry. All right. So we want dy dx. I've got this big, messy, sloppy thing, but it's got some dy dx's in it. So let's try to solve this big apparatus here for dy dx. In service to that, I'm going to distribute this negative and clean some things up. We've got 3x squared minus y squared minus 2xy dy dx plus 3y squared dy dx equals 0. And then the way we solve something like this for dy dx is just push everything that doesn't have a dy dx to the other side. So this term doesn't have a dy dx. This term doesn't have a dy dx. Both of these terms do. So I'll leave them over here and push the other guys over. That'll give me negative 2xy dy dx plus 3y squared dy dx equals, add this over, so it's y squared, subtract this over, minus 3x squared. And then on the left-hand side, I can factor out dy dx, and I get negative 2xy plus 3y squared dy dx equals y squared minus 3x squared. And then we can divide over by this piece. So dy dx to y squared minus 3x squared divided by negative 2xy plus 3y squared. And that's job done. And you notice that this is an implicit expression also, right? It involves both x and y. Because I cannot solve this original for y, I can't like plug in for the y's here. I just have to leave it as this implicit expression.
Question. How are we able to look at that original expression and just know that we will not be able to solve for y?
It's a good question. So I'm being a
like
little
knowing myself,
disingenuous
I would
there.
attempt
It is possible. It's just not easy. You're not going to get there through regular algebra tricks. And the way I can do that is just by imagining trying to do the regular algebra tricks. Normally, you try to isolate the y terms, which would mean you'd leave these guys on the left, push this guy back over to the right, and then try to factor out all of your y's. But because the power of y here is 2 and the power of y here is 3, when I do that, I can't like factor out a straight power of y and just have x stuff left over. So anything that would allow me to solve this is going to be pretty complicated. So this is a cubic equation when you think of it in terms of y, it's a cubic, and it is possible to solve any cubic, but it's not at all pretty. And it's still not really explicit in the sense that there's lots of pluses and minuses involved. So the thing that kind of tells me that I can't solve this for y, at least not easily, is that I have two different terms with y's, and the power of y in each of those terms is different. That's kind of the hint. But really just imagine trying to do it. Sometimes expressions like that you can still work with. But just imagine trying to go through the normal like isolate, factor, divide thing. And if it doesn't look like it's going to pan out, probably it would.
Okay. Will you generally tell us explicitly, as it were, whether or not you want us to? Because, for example, for that end expression, I would immediately begin looking back and see like, oh, can I put y in for something? Would you generally let us know when to not attempt it?
If an implicit answer is acceptable, say for on a test, I would tell you, yeah. And the book problems, the homework problems will say, either they'll tell you to either find an explicit expression or they won't command you to do either. And if they don't command you to do either, then an implicit one is okay. But yeah, you'll be able to infer from the problem.
Perfect, thank you.
All right. There are some other fun things we can do with these. So one of the reasons why implicit differentiation is so nice, like that circle, you'll notice that all of these curves here fail the vertical line test, which means that y is not globally a function of x, but it is locally, right? So if I were to just look at this little portion of this lemniscate in problem 31 here, just this little portion where that point is, we could say that just this little piece passes the vertical line test. And that's what the implicit function theorem is saying. I would love to go into detail about the implicit function theorem, but I think it might be asking a bit too much. So instead, let's see if we have one problem or two to round up with. Yeah, let's do something where we're finding a second derivative. Find y double prime. Find the value of y double prime at the point where x equals 0. Let's do number 39. So I've got xy plus e to the y equals e. Y plus e to the y equals e. And we want to find y double prime at the point where x is equal to 0. All right, we can take a look at this curve. I have no idea what that thing looks like, probably a little wonky, but we can graph it. Here it is. Pretty weird. Definitely not a function of x everywhere, right? Fails the vertical line test over here. But if I zoom in and just look at this piece, then that piece does implicitly define y as a function of x. So I'm kind of ignoring everything down here. So what I'm doing is looking for the second derivative at this point. So first we should find that point. I just kind of cheated there. Let's find the point on the graph where x is equal to 0. To do that, I would plug in 0 for x here and solve for y. So I have 0y plus e to the y equals e. In other words, I just have e to the y equals e. And you can solve this by taking logarithms. So the ln of e to the y will be equal to the ln of e. And the natural log of e to the y is just y. So y is equal to the ln of e, which is 1. So the point is 0, comma 1. In other words, when x is 0 along this curve, y is equal to 1. That'll be useful as we go. Now, let's find y prime. To do that, I apply the operator ddx to both sides. ddx of e is 0 because e is a constant. And over here on this piece, we're going to need some product rules. So that's going to be 1 times y, or just y, plus x times the derivative of y, which is y primed. So that's the derivative of x times y. And then the derivative of e to the y is e to the y times y primed.
I have a question because you 0 multiple y's already get the 0, but why the ln of e to the y is equal to ln of e the top, and you get the y is equal to ln logarithm e is equal to 1.
Yes. Yeah. So what's going
Why
on?
did you put the y at here again?
Well, the ln of e to the y is y. So I'm simplifying this. All right, remember the definition of the natural log. One way you could define the natural log is that the ln of e to some stuff, whatever that is, this is always just equal to that stuff. So the ln of e to the y is just y. So this term, ln of e to the y, simplifies to y. And the ln of e over here, I just leave that alone. That is the ln of e. But the ln of e is the number 1. So it's a function value that we should know. We should know that the natural log of e is equal to 1. And then the ln of e to the y is going to simplify to e to the y. So we're just asking, how do we solve equations like this? We solve them by taking the natural log of both sides and then simplifying as much as we can. If it feels better, we can do these one at a time. Instead of saying like that is equal to 1, I could then in a separate line say, okay, so y is equal to 1 like this. All right, so that way I'm just simplifying the left and simplifying the right. Okay. All right, I'm going to keep going because we still have a good amount of work to do. We need to find y double prime. I have here this expression, which has some y primes in it. If I want to, I could try to isolate y prime and then differentiate that again. But I know I'm using implicit differentiation anyway, so there's no need to isolate the y prime here. I can just apply ddx to both sides again. The only thing I might do is combine these two terms. So I'd say this is the same as y plus x plus e to the y times y prime.
The top you get y is equal to 1. How did you get the find y prime and the ddx parenthesis xy plus e to y? How did you get that equation again?
So these guys I differentiated using the product rule. That's this. So this is like 1 times y plus x times y prime because the derivative of x is 1. And then the derivative of y is y prime. So this was a product rule.
Is it ddx parenthesis xy plus e to y parenthesis? This one is you set and questions at here. It doesn't depend on the top those answer.
No, yeah, I haven't used this at all yet. I will use this eventually, but I have not used it yet.
Okay.
All right. So now I've got this expression, which has a y prime in it. So you know what? I'm thinking we probably will actually have to. Yeah, let me go ahead and solve this for y prime just so we have that. But I won't work from there. I will work from this line on the next piece. So if I solve this for y prime, I'm just thinking ahead. I'll need it eventually. I can subtract this y over and then divide by this. I get negative y over x plus e to the y. So we'll just tuck that in our pocket. And now we're going to find y double prime. So to find y double prime, I'm going to work from here and I'll apply d dx again. I could also work from up here if I wanted, but I don't want. Again, the right-hand side, d dx of the constant is going to be 0. On the left-hand side, d dx of y is y prime, and then plus. Here again, I'm going to need a product rule, and this time the product rule is going to be a little more complicated. I differentiate x plus e to the y, and that will give me 1 plus e to the y times y prime. And I leave the y prime alone. And then I leave x plus e to the y alone. And I differentiate y prime, I get y double primed. And on the right-hand side, d dx of 0 is 0. So here I'm using a product rule on these, or to get these. And now maybe you see why I chose to take this extra step and find y primed over here, because I knew that I wouldn't just get y double primes in this. I'm going to have y primes in it as well. And since we want y double primed, I'm going to need to plug this in both here, here, here. A dog. So now if I plug in for y prime, I have negative y over x plus e to the y plus 1 plus e to the y times negative y over x plus e to the y plus times y prime, which is negative y over x plus e to the y plus x plus e to the y times y prime equals 0. Okay, now there's no more y primes, just y double primes and y's and x's. It's a bit messy looking, but that's okay. Remember what we want. We want to know what is y double prime at the point 0, 1. So now I plug 0 in for x and 1 in for y. So plugging x equals 0 and y equals 1, I get negative 1 over 0 plus e to the 1 is negative 1 over e plus 1 plus e to the 1 times negative 1 over e times negative 1 over e again plus 0 plus e y prime prime equals 0. which we can solve for y double prime. It's not too bad. This is negative 1 over e. Plus, if I distribute this 1 over e term here, what do we get? This will be write this minus 1 over e. And then e times negative 1 over e, this piece is negative 1 times this is going to be plus 1 over e plus e times y double prime equals 0.
On the top, your process on the top, you already get y is equal to 1. So here you just plug the 1 into the y, right? So it's equal to minus 1 minus y over x plus e to the y is equal to minus 1 over e.
Right. Yep. This is.
And also x is
0.
equal to 0.
Right. Yep. So I'm in this expression right here. I'm plugging in 0 for x and 1 in for y. I'm doing both of those at the same time because I know that that is my point. And this is what we get. It's pretty gnarly looking. These two middle terms here came from distributing this to here and to here. So negative 1 over e times positive 1 is this negative 1 over e. And then e times negative 1 over e is negative 1 times this is positive 1 over e. So these guys cancel, right? These guys give me 0. And I get negative 1 over e plus e times y double prime equals 0. So if I solve that, I can add 1 over e to both sides. It gives me e times y double prime equals 1 over e. And then divide both sides by e. So y double prime is just perfectly going to fit as 1 over e squared. It's quite a bit of work. It's quite a bit of work. But it's manageable. All right. This is about as bad as these problems are going to get for us. But there's lots that we can do with implicit differentiation that we couldn't do without it. Specifically, this thing called related rates, where I want to take some objects that are connected to each other through geometry, but changing over time, like a balloon that's inflating or a ladder that's like sliding down a wall. I can look at some of the geometric quantities there and ask how are those changing over time. The geometry will give me an equation that I can work with, and then you differentiate through that expression with respect to time, and you'll be able to get some really useful rates of change, like how fast is the balloon inflating, or how quickly is the top of the ladder sliding down the wall, all that sort of stuff. So that's where we're going with this. The implicit differentiation is neat from a math standpoint, but it's really neat from a physics standpoint. So that's the path from here forwards. We will be kind of looking at some physics problems. It'll also allow us to differentiate logarithm functions. So for our next class, for for Monday next week, I encourage you to review your rules for logarithms and review your rules and definitions for inverse trig functions. Those are some things that maybe people get a little rusty with, that we will be working with a lot in the coming days. That's it for me. That's all I've got for you guys today. This is how you differentiate implicitly. We will be building from here. So next time we're going to talk about derivatives of log functions, logarithms, and then we're going to talk about related rates. And we'll do both of those things on Monday of next week. I'll have your tests back for you no later than Wednesday next week. If you have anything you want to talk to me about, questions, whatever, you know where to find me. I have an office hour this afternoon. You can message me on Canvas. You can come by the Discord. Is there anything you guys would like to talk about now before we get scooching? Yeah, Sarah, I see you had a...
There was some of the math that didn't make sense. Give me a second. I'm going back, tracking back. Boy.
So where do we get lost?
Oh, so okay. Well, wait. Move your mouse down slightly. There. Okay. So in that line, you have a 1 plus e to the y times negative y over x plus e to the y. I think if if it's the same way it was earlier in the problem, the 1 plus e to the y, are they both being multiplied by negative y over x plus e to the y?
Yeah, so this y prime right here is this negative y over x plus e to the y. And this y prime right here is this negative y over x plus e to the y. So the second y prime is outside the brackets. If you want, maybe it would help. Let me convert these to brackets because that way they match the next line. That might help see a little bit where everything's coming from. This one is this one. This e to the y is this e to the y. And this y prime I'm plugging in here. And then outside of that,
Oh, okay.
I've got this y prime that I'm plugging in here.
So when I'm getting the derivative of e to the y, I have to do the thing where I treat y as a function of x.
Yep. Yeah,
Okay.
when we
Okay.
differentiated to get this, we got this extra y prime inside from the chain rule, or from the implicit differentiation.
Yeah. Okay, thank you. That was it.
Of course. Any other burning questions before we get scooching for the day?
Professor, will you have office hour this afternoon?
I do have an office hour this afternoon, but it's going to be like Wednesday was. So I'm giving makeup tests in this office hour, which means I'll be kind of busy. But if you want to ask questions, we can come type to each other in the chat. Because I will be proctoring makeup tests during this office hour, I can't like do the normal thing where I come in and solve problems because I need to be quiet so they're not disturbed. But
Makeup test is for our class. Is it the makeup test for our class?
Yes, I am doing makeups for our class, but only for people who missed the test. So if you didn't take the test on Wednesday, then today is the last chance to come take the test.
Okay, that's. And after we already grade the score. After that, will you teach us about the exams questions again? Because I think I missed some question.
Yeah, as a general rule, I'm not going to solve every problem from the test in class, but if there's a problem that you want to see or two problems that you want to see, I'd be happy to do those in class.
Thank you.
Of course, of course. Alrighty, guys, I'm going to go ahead and sign out here. If you do need to see me or talk to me for anything, you know how to do it. And I will see y'all on Monday. Today will be the last day. No, yeah. So if we've made other arrangements, then that's okay. Yeah.
Okay, cool. Thank you.
Alrighty, gang. Take care.